All right, so today what we're going to do is we looked at power series and we played around with them, but today we're going to see how to build one, okay? So you can take any equation and turn it into a polynomial, and most of the time what we use these for are like the transcendental functions, which I mentioned last time. So like your e to the x, your sines, cosines, you know, our trig functions. You can do it with technically any function, but those are the ones we use it the most for. And then once we see like the root series of like how to build it, then what we do is we take those series and we manipulate them to create series off existing functions. So I don't think we'll do much of that today. That'll probably be Monday after the break. I'll show you guys how to manipulate an existing series to get what you want. Because for those of you that are going to see Taylor and McLaurin series in other classes, that is what you're going to be asked to do. Okay, you're going to be asked to take an existing sine series and then turn it into sine of x squared, or turn it into a wave equation that you need. So these are actually, like I said before, very, very useful. So let's look at, let's start with something really simplistic, right? So if we want to take the function e to the x, and I want to write it as a Taylor polynomial. So let's do a first degree polynomial. All right, now there's a notation that you'll see a lot if you look at any of the web work problems, and it's going to be something like this. So p sub n of x, n is the degree of the polynomial, right? And what we mean by degree is the highest power of x that you see. So the series is going to give you the infinitely long polynomial. It's going to take n all the way to infinity. But sometimes we'll say, well, just give me degree 5. So then you would generate the series up till you get x to the 5th, and then you would stop. All right, so one of the things you'll do, and we're going to look at it today, is we're going to find out the remainder, how to find out the remainder term. And then if we, like I was mentioning before, if you're in a situation where you only need to approximate e to the x within like 1% accuracy, there's actually a calculation we can do that'll tell us what degree n we can stop the polynomial with, and then we can just work with the finite polynomial. You're going to find in like physics and some of your upper level classes, when you see this again, typically 3 to 4 non-zero terms is usually all they'll ask you to generate. But you'll see with some of these polynomials, like sines and odd function, cosines and even function, right? So for sine, you're going to see that all the even terms, the coefficients are 0. And you're going to see for cosine, all the odd coefficients are 0. So when we say 3 non-zero terms for a sine function, you're going to get x to the first, x to the third, x to the 5th. So pay attention when you're asked to generate a finite polynomial about whether they want x number of non-zero terms or degree n. Those are two different things. So if I tell you to take sine of x to the 5th degree, well, that's actually going to end up only being the first 2 terms, or excuse me, the first 3 terms. But if I tell you to take sine of x to degree 3, you're only going to end up getting the first 2 terms out of that. So just make sure that you're paying close attention. But let's see how to do this. So if we want to take the first degree polynomial, you'll notice that it makes a lot of sense for some of these functions to build them around a value that we can easily evaluate. So for e to the x, the obvious choice is x equals 0, because we all know e to the 0 is 1, right? For ln of x, the obvious choice would be 1, because everybody knows ln of 1 is 0, right? Sine, cosine, we typically build around 0, but in theory, I can build it around any x value that I want. And we talked about on the last section that the value you build it around, right, that's called the center. So that's what comes out in the interval. So I'm actually going to show you some pictures today, too, that's going to show you what the polynomials, the series is actually doing and how it turns into the original function. So if we want to do the first degree polynomial, what we want to get is, right, we're going to have an x to the 0 term. So just to be thorough, I'm going to write that. Even though x to the 0 is 1, we would just simplify that into a naught, right, plus a1 x to the 1. And so in order to build the first degree polynomial, I mentioned last time too, this is just really finding the equation of the tangent line at that point. So if we find the value of 0, we're going to get e to the 0, which is 1. Then we know that if you have the equation of a line, a1 is actually the slope. And we get the slope by taking the derivative. So the derivative of e to the x is just e to the x. So f prime of 0 is also 1. So if you're building a Taylor polynomial of e to the x centered at 0, well, all the derivatives are e to the x. So every time you plug 0 in, you're just going to get 1, 1, 1, 1, 1. So all the coefficients of this polynomial would be 1. If we did e to the x squared, right, the derivatives would change a little bit because then you would have to do the chain rule. And so what you would see that if you did e to the x squared, the derivative would be e to the x squared times 2x. So then if you plug in 0 into the derivative, you would actually get 0 as your coefficient. So you would see some terms get skipped potentially. All right, so if we look at this function, right, generating the Taylor series, and we simply fill in, right, this is our A naught, this is our A1, we see that P1 of x is just 1 plus x, because a to the 0 is 1 times 1 gives you 1, and then we plug in a 1, x to the 1 is just x. So if we actually look at this on a graph, e to the x is here, and what we just found was the tangent line at 0. So if I go to the second degree polynomial, we're going to get a quadratic, and we know a quadratic, right, has a bend in it. So what you're going to see is every time we increase the degree of the polynomial, we're going to get more and more bends, and eventually the polynomial will fold right along this line and actually equal our function. So if we look at the second degree polynomial, right, we already said the coefficients are going to be 1, but in actuality, there's a little extra step. So the second degree polynomial is here. And I'm going to go out one more and show you the third degree polynomial. So there's a pattern, a very clear pattern emerging here. So when you've been doing tangent line approximations, there was actually a denominator that no one ever really showed you before, okay? And the reason we never showed you is because when you look at the first two terms, the denominator ends up being 1 each time. So there was no reason to write it. So if I want to know the nth polynomial of this function, well, the derivative is just 1. I would get x to the n over n factorial. So what's actually happening in this polynomial is that this is technically 1 over 1 factorial, but 1 over 0 factorial, but 0 factorial is 1. This is 1 over 1 factorial, but 1 factorial is 1. And then we get 2 factorial. And when you look out at the third degree, that's actually 3 factorial. So if you want to write the series, or the power series of e to the x, if we want the infinite series, we go from 0 to infinity of x to the n over n factorial. So let's look at the definition of a Taylor polynomial. And you'll see why that coefficient comes up. All right, so the formula or the algorithm that we're really using to do this is if you want a center at any value c, we're going to get f of c, should be a c, plus f prime of c times x, plus the second derivative of c, I made a mistake. That should be x minus c times x minus c squared over 2 factorial. And when we get to the nth term, it's the nth derivative evaluated at c times x to the c raised to the n over n factorial. So technically, the 0 factorial and 1 factorial is there, right? So if you just want to be thorough in your formula, so you can see it, you can write it as well. Now, if we look at e to the x, all the derivatives are the same. So f prime of c, if we center at 0, was 1 every single time. So we got 1, 1, 1, 1, right? That's why the series just has the coefficient 1 over n factorial. The c term was 0, so x minus 0 is just x. That's why all we saw was x to the 1, x squared, x to the n. If we want to center it at 0, right, we could adjust the formula, and most Taylor series are centered at 0, with the obvious exception of things like ln of x, which it makes more sense to center at 1. But if we want to center it at 0, and notice I don't put in 0 for x, I'm only putting in 0 for c. This just simply becomes f of 0 over 0 factorial plus f prime of 0 times x over 1 factorial. The second derivative evaluated at 0 times x squared over 2 factorial, all the way up to the nth derivative evaluated at 0 times x to the n. So the original function, think of that as the 0th derivative, right? So if you plug in, this is technically, so these count up 0, 1, 2, all the way to n. If we take it all the way to infinity, then we generate the actual series. So let's build a Taylor series using this definition for something like ln of x, all right? So all you need to do is take the derivative out as many times, build as many of the coefficients till you see the pattern. Once you recognize the pattern in the coefficients, you can stop taking the derivatives and you can just build the series because it's going to follow this format. All right. So let's do an example. And let's build the Taylor polynomials 0 through 4. Oops. And we're going to center it at 1 because ln of 1 is a known quantity. So since we know we're going to go all the way up to the 4th degree eventually, what I would do is be really systematic with your work, okay? So f of x, right, is just ln of x. The first derivative is 1 over x, which I'm going to write as x to the negative 1, because that's just going to make it easier for me to take the next derivative using the power rule. The second derivative, right, is negative x to the negative 2, which I'm going to take back with a positive exponent because I want to make sure I can see the pattern that's emerging, right? The third derivative, we can see here, we get negative 2 times negative 1. That gives me positive 2, x to the negative 3. So this is 2 over x cubed. And then we'll take the fourth derivative, and it's really up to you when you want to stop using little tick marks, but you can actually just write the number in there as well. And this will be negative 6, x to the negative 4. So I'm going to get negative 6 over x to the 4th. So what do we see happening in those numerators after you take the first derivative? It goes 1, 2, 6. Right, see the pattern that's happening? What are those? N factorials, right? And what's great is, well, it's not great, but what you notice is the factorial is 1 less than the power. So this is 1 factorial, right? This is 2 factorial, but x is to the 3rd. This is 3 factorial, but x is to the 4th. So we're going to need that when we actually write the generic series in a minute. All right, then I have to evaluate all the derivatives at the center. So we'll do that over here. So f of 1 is just 0. F prime of 1 is 1. F double prime of 1 is negative 1. The third derivative evaluated at 1 is 2, and the fourth derivative evaluated at 1 is negative 6. So now we can build our polynomials, okay? Oh, sorry, question.
Wouldn't f double prime be positive?
Yes. Wait, no, because f prime is here, f double prime is here, yeah. No, you're all right. So if we want to build these polynomials, right, the first one says build P0 of x. Well, P0 of x is just the very first term. That's it. And it equals 0. So it's 0 times x to the 0, which is just 0. The second, or the first degree polynomial says grab the first 2 terms. So it's 0 times x to the 0 plus 1 times x. Oops, and we centered at 1, so it's actually x minus c. So there is the first degree polynomial, because it's just 1 times that. When you build the subsequent ones, you just repeat what you started with and add the next term. So the first non-zero term was x minus 1, and our coefficient for the second derivative was negative 1, so I get negative x minus 1 squared. Now, this x minus 1 was over 1 factorial, which is just 1, but this x minus 2 is over 2 factorial. Excuse me, x minus 1 squared is over 2 factorial, because that's what the algorithm says. Take the derivative of that value and put it over n factorial. All right, so let's build the third one. So the third one, I just grab everything I have so far. Now notice I'm putting x minus 1 in parentheses, because you need to be able to see the center in the equation. So you need to make sure if you're centering it something other than 0, you're locking that value with x every time. So this is going to be negative, and I'm just going to do this so we can see this pattern emerging. My next coefficient was positive 2. That's over 3 factorial, and this is x minus 1 cubed. So all we're doing in each term, derivative, third derivative, you can tell which derivative by the power, third derivative over 3 factorial times this raised to the third, right? So that means the fourth polynomial my coefficient was negative 6. That goes over 4 factorial times x minus 1 to the 4th. So let's see visually what we're doing. All right. So here's our 4 polynomials. Now I want to show you the graphs of those first 4 polynomials. So the solid black line is ln of x. Now this is a great thing to do, is I told you guys before about Desmos. Right? And a really, really useful thing on Desmos to do when you're building these polynomials is graph the function, because Desmos will let you do as many graphs as you want, and they're all color-coded, and it'll show you which one's which color. But what a really cool thing to do is graph the original function, then build the polynomials, slowly increasing the degree just like we did. And all you got to do is do 3 or 4 of them. And then graph them all on top of each other. So what you saw with degree 1 was all we got was the tangent line, just like we expected. So if we wanted to approximate ln of x from this, we don't have a very big window of values you can plug in, because by the time you get over here, right, and over here, the line's too far from the curve, right? But then the next thing was a quadratic. So the quadratic, right, was x minus 1 squared, right? And if you look at it here, look how much longer it hugs the curve before it drips away. But look where it crosses. It crosses at 1, 0. So that's what the center does. The center, all of these polynomials are going to be tangent to the curve, right, at that point. But then as you go, the first one is just tangent, right? It's got 1 point. But then as we increase the degree of the polynomial, you're going to get more and more values of x around your center that are good. And then look at the third degree. The third degree creates another bend for us, and it hugs it even longer before it goes away, right? And then if you look at the fourth degree, that creates another bend, but it hugs it even longer. So what you're doing is you're increasing the neighborhood around the center that you can use this function for. And if we actually graphed the infinite polynomial, the entire Taylor series, you would see that it would actually just overlay the graph completely. But you can't plug that into a computer because you'd have to plug infinitely many things. So every time, if you guys remember way back in algebra, right, when we were learning structures of graphs, every time you up the degree of a polynomial, you're creating more bends, twists, and turns, and more opportunities for it to really hug the curve that you want to create. All right, so let's look at another one. Let's actually build cosine x. And then we're going to use cosine x, our series, or our polynomial, excuse me, to approximate a value. So we're going to let f of x be cosine x. And remember, cosine's an even function. So I mentioned before, you're going to see all the odd terms are going to disappear. So we can't build 0, 1, 2, 3, 4. So we're going to build the 0th, the 2nd, the 4th, and the 6th. And then we're going to use P6 to estimate cosine of 0.1. So clearly, if we want to estimate 0.1, and I already kind of gave you a heads up, like, we all know what cosine of 0 is. So it makes a lot of sense to center sine and cosine around 0, because that's a known value. So we're going to center this at 0. So just like we did before, I'm going to build the derivatives. So the original function is cosine. The first derivative is negative sine. The second derivative is negative cosine. And the third derivative is positive sine. And what's the fourth derivative going to be? Cosine. You get it back where you started. So sine and cosine repeat in 4 cycles when you do the derivative. So once you've built this, 0, 1, 2, 3, if I asked you for the 15th derivative of cosine, well, you've got 0, 1, 2, 3, right? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. The 15th derivative would be sine. So if you know the cycle repeating, what you can do, if I said what's the 16th derivative? Well, 16 is divisible by 4. So you have a remainder of 0, so it takes you back to the original function. So the fast way to count this is think of this 0, 1, 2, 3 as the remainder when you divide by 4. So if we did the 15th derivative, well, when you divide 15 by 4, you get a remainder of 3, third derivative, sine of x. If I said what's the 2001st derivative? Well, 2000 divided by 4 has a remainder of 1. So f prime, it'd be negative sine x. So you can actually, using sine and cosine, all you have to do is build these, and if you divide by 4, whatever derivative you're looking at, that matches the remainder when you divide by 4. Does that make sense? Okay. So I don't actually have to take this all the way to the 6th derivative, because I know it's just going to cycle back around, right? Now let's plug in our value. So f of 0, cosine of 0 is 1. f prime of 0, well, sine of 0 is 0. F double prime of 0 is going to be negative 1. And f triple prime of 0 is going to be 0 again. So look what's going to happen to our coefficients. All the even terms, or excuse me, all the odd terms have 0 coefficients, which makes sense because cosine's an even function, right? And the coefficients you're left with are going to alternate between negative 1 and 1. So both sine and cosine are going to have this property, except when we do cosine, you're going to see all the even terms have coefficients of 0, and the odd terms go back and forth between negative 1 and 1, okay? So they're both alternating series. So let's build our polynomials. So we want to build the 0th one first. So all we do is take the coefficient at 0, right? Put it over 0 factorial and multiply it times x to the 0. So it just simplifies to be 1. You just get a horizontal line. Now if we look at the graph of cosine x, right? That makes sense because look at the tangent line at x equals 0. The tangent line is going to be a horizontal line that intersects at 1. Right? So the first degree is always going to be your tangent line. Right? The second degree polynomial, right? We know that first term is 0. So right, we're just going to grab the 1 and then I'm going to add it to negative 1 over 2 factorial times x squared. So it takes a while to memorize the pattern, but it is really a simple algorithm. You just take the derivative, put it over its factorial, and then multiply it times the power, right? The fourth polynomial, right, we'll take what we had before. So if we look at this, right, the next coefficient should be 1 because the 1 and negative 1 just keep going back and forth, back and forth. So I'm going to have plus x to the 4th over 4 factorial. So what's the next term going to be for 6? Should it be positive or negative? Negative. And you're going to get x to the 6th over 6 factorial. So if cosine's an even function, it makes sense because if you sum an odd and even function, right, then it becomes a neither, right? But if you sum all odd terms, you get an odd function out. If you sum all even terms, you get an even function out. In the very first week of class, when we were doing our Calc 1 review, and I showed you that really cool trick for integrals, right? If you have symmetry and you're going around 0, right? We said, well, if it's odd, the positive area above equals the negative area below. So if you were integrating from negative a to a, we got to call that 0, right? If you had an even function, well, then you had symmetry around y, and so you could simplify your integral to just 0 to a times 2. You could just double that area. So the same thing holds when you're making these polynomials. If you know that you have an odd or an even function, the polynomial should reflect that. So if you're not getting that, you know you've probably done the algorithm wrong, and you want to make sure you check. Now, ln of x is a neither. Doesn't have any symmetry. E to the x doesn't have any symmetry. So we're going to get every single term when we generate those polynomials. All right, so now let's use this to estimate cosine of 0.1. So cosine of 0.1 is approximately, it can't be equal unless you use the entire series. So it is approximately 1 minus 0.1 squared over 2 factorial plus 0.1 to the 4th over 4 factorial minus 0.1 to the 6th over 6 factorial, and that works out to be 0.995004165. And so it makes a lot of sense that 0.1 should be really close to 1 because cosine of 0 is 1. So it's not exactly 1, but it's much, much easier to type in a polynomial, especially if you're using a computer, than it is to deal with the cosine function itself. So if you ever have to go out like 10, 20 decimal places for some reason because you need a lot of accuracy, the polynomial helps you do that. All right, so let's build sine x. And this time, let's center it around pi over 6, just for funsies. So pi over 6 is about 30, it is 30 degrees. And on the unit circle, we know that at theta equals pi over 6, the point on the unit circle is 1/2 square root of 3 over 2. So that means anytime we have to deal with cosine, we're going to get back a half. And anytime we have to deal with sine, it's going to return square root of 3 over 2. All right? So let's build our derivatives first. And I don't really have to think about this if I don't want to, because I'm starting with sine, and I can just loop back and copy the other 3 terms on the list in order, because they loop, right? Because remember, the derivative of that would take you back to that anyway. So if you're doing multiple problems, you know, you don't have to reinvent the wheel, although you should know these derivatives. So if you take the derivative of negative cosine x, you end up right back at sine. So that same trick works. If you need the whatever derivative of sine, divide the number by 4, whatever the remainder is, grab it off the list, and there's your derivative at that point. All right, so let's look at this evaluated at our center. So f of pi over 6, that's sine, so that's square root of 3. Oh, my bad. I got my point backwards. Nobody caught me. Y'all don't have your unit circle memorized? No, everybody's like, no, it's 2. No. So sine of pi over 6 is 1/2. F prime of pi over 6 is cosine pi over 6, and that's square root of 3 over 2. The second derivative at pi over 6 is negative sine pi over 6, so that's going to be negative 1/2. And then the third derivative of pi over 6 is negative cosine pi over 6, so that's negative square root of 3 over 2. So there's a very clear pattern emerging for our coefficients. We're going to get positive 1/2, then positive square root of 3 over 2, then negative 1/2, negative square root of 3 over 2, and then it'll loop back around. So what you're going to have now are 2 positive terms, 2 negative terms, 2 positive terms, 2 negative terms. So, and the reason we're getting this different is because we're centering around pi over 6. If we centered it at 0, then it would be symmetric, the equation we would do would be symmetric to the origin, and we would only return the odd values. We would get the zeros just like we did before. But if you move the center, it adjusts the polynomial, because every degree polynomial we generate is going to touch the graph at pi over 6, right? Because that's what the center does. So now let's build the third degree polynomial. So the first coefficient is 1/2. You would put that over 0 factorial, which is just 1, and then you'd multiply it by x to the 0, which, or x minus pi over 6 raised to the 0, which is still 1, right? The second coefficient is square root of 3 over 2. That would go over 1 factorial, which is still 1, and we multiply that by x minus pi over 6. So just like we did with ln of x, if you change the center, you got to make sure you reflect that. Then it gets negative. I get negative 1/2, but I'm going to divide that by 2 factorial, so 2 factorial will end up in the denominator. And this will be multiplied by x minus pi over 6 squared. The third degree, we have negative square root of 3 over 2 divided by 3 factorial. So when you divide by the 3 factorial, it's going to end up in the denominator, times x minus pi over 6 cubed. So I want to show you what the 2 polynomials we just built look like compared to the graph. Well, everybody get this copy down first. So what would the next term be? Anybody want to take a guess?
1 over 2 times 4 factorial.
Mm-hmm.
X minus 6 pi over 6 to the 4th.
That's exactly right, right? So the coefficient would just loop, and so if we wanted the fourth, right, it would be positive 1/2 over 4 factorial raised to the 4th. Then we'd get positive square root of 3 over 2 over 5 factorial, and that same term raised to the 5th. So the pattern would just continue and continue and continue. All right? So here's what this looks like. So here's the graph of cosine of x. That's the solid line. We built a 6-degree polynomial, and when you map it over it, look how long open the neighborhood is now. I mean, we can go all the way from basically negative pi to pi to use that guy if we want to estimate values. So this was centered at 0, right? But what we just did was we took sine of x and we centered it at pi over 6. So you can see they've dotted the center here. So this is what the polynomial was built of. So the polynomial doesn't have symmetry anymore because it shifted over. So that's why we were getting all the powers returning. But if we had built it around 0, then it still would have had that odd symmetry to the origin like we had before, and you would have seen those even terms disappear. So you can see here that if you only go to the 3rd degree polynomial, you have a window of actually a little to the left of pi over 2 to about pi over 2 that this graph is pretty good for. And then if we needed to go over to pi, well then I would need to up the degree of my polynomial. Okay? So we good? Okay. So what is a Maclaurin polynomial? So don't freak out. It's exactly the same as a Taylor polynomial, but the center is always 0. So if someone says build the 5th degree Taylor polynomial, they have to provide the center. But if they ask you to build the 5th degree Maclaurin polynomial, center 0. All right. So let's look at one for the function ln of 1 plus x. So just like before, so here's what I'm going to do. The derivative of this is 1 over x, but to make my derivatives easier, I'm going to write 1 over x, right, as 1 plus x to the negative 1. So really, this is this, but I just want to be able to use the power rule here. And not only is it a power rule, it's technically a chain rule, but what's the derivative of the inside of that function? 1. So this will be pretty easy to do, right? So the second derivative will be negative 1 plus x to the negative 2. So we get negative 1, right, over 1 plus x squared. The third degree, and the reason, guys, that I'm going back to this, I'm doing this to make the derivative easier, but the reason I'm going back to this, you can't have negative exponents in your polynomial. For the definition of polynomial, all the exponents need to be positive. And the x terms will be, but we don't want negative exponents in our coefficients either. So it's just a good idea to bring it back to this when you actually go to plug in your values. So the third derivative is going to be negative 2, 1 plus x to the negative 3. So that gives me negative 2 over 1 plus x squared. And are you guys seeing? Huh? No. Yes, because you guys are smarter than me today. Okay. So is anybody noticing where the factorials might be coming from? You see what's happening in these coefficients when we keep taking derivatives? You see what keeps happening? So when you take the derivative, you multiply by 1, right? And then it gets changed to a 2. And then the next time you do it, you're doing 1 times 2. And then it got changed to a 3. And then the next time you're doing it, you're doing 2 times 3, but that 2 is really 1 times 2 times 3. And then when you do it again, you're going to bring the 4 down. And so you're really doing 1 times 2 times 3 times 4. So every time you take the derivative, right, the coefficient comes down front, but it's still there. It never goes anywhere. So you can see, and when you actually look at the proof of the algorithm, you can see where that factorial comes from. So sometimes, if you have a function like this, where you can use the power rule when you're taking the derivative, you'll actually notice that you might produce a factorial in the numerator as well. So, and then when we go to write the actual series, which I'm going to show you in a minute, how to take this pattern you're seeing and write the infinite series, you'll see that sometimes the factorial in the numerator will simplify with the factorial in the denominator, right? But that's what's happening here every time you up the power. All right, so this says evaluated at 0. So this is pretty easy to plug in 0. So ln of 1 plus 0 is just 1, so ln of 1 is 0. G prime of 0 gives you positive 1, right? All these denominators are just going to come out to be 1 because you're just going to be saying 1 plus x or 1 plus 0 raised to some stuff, which will always be 1. So these are just going to return the numerators. So if we build our 4th degree polynomial, the first term is 0, so we get 1 times x, then minus 1 over 2 factorial x squared, plus 2 over 3 factorial x cubed, minus 6 over 4 factorial x to the 4th. So when you're building a finite polynomial, I'm actually okay if you leave it in this form, but if you want to work with it, we usually simplify it down a little bit. So we know that 2 factorial is just 2. 3 factorial is 6, and 2 over 6 is a third. And then 6 over 24 is going to give you a fourth. And the reason you want to simplify it down is if you're actually going to use this to estimate values, trying to type factorials in your calculator and trying to deal with that can be a pain. Plus we can see it simplifying down. So if we want to use this to approximate ln of 1.1, well, ln of 1.1, remember our original function was ln of 1 plus x. So really what we have here is ln of 1 plus 0.1. So do I want to plug 1.1 or 0.1 into my polynomial? 0.1. So look at the original function, right? X was the variable, right? So our original function, if it were ln of x, I'd just plug in 1.1. But because our original function we built was 1 plus x, I really only need to plug in 0.1 into the polynomial. So this is our 1 plus x. So this is going to be approximately equal to P4 of 0.1. So you'll get 0.1 minus 1/2 times 0.1 squared plus 1/3 times 0.1 cubed minus a fourth times 0.1 to the 4th. And that's approximately that. Which is not too far off from 0, because 1.1 is pretty close to 1, and ln of 1 was 0. So it kind of makes sense. So we've only really built finite polynomials up till now, right? So let's talk about the series as a whole, all right? So the series, right, is approximating a function, and all we've done so far is build some finite nth degree polynomial. But the function has to be the infinite series for it to be truly equal. So any terms beyond n, so like up here we only went to 4. So 5 through infinity, we call that the remainder. So we kind of looked at the remainder a little bit earlier when we were trying to say, could we estimate the sum, right, of an alternating series? And we said, well, if we just grab the first n terms, the remainder should be pretty close to the next term if they're passes the alternating series test. So f of x, if you plug it in, represents the exact value of the function. P of x, right, if we just pick a finite n and use that, that's the approximate value of the function. And this is the remainder of what we're missing. So the remainder is also sometimes referred to as the error. It's how far off are we. So if we rearrange this equation in the same way we did for our partial sums, we can actually say, right, if I solve this for the remainder, I can say the error is equal to the absolute value of the remainder. And the reason we use absolute value is some of these terms are positive, some of these terms are negative, and I don't know what the remainder is going to add up to. So we always look at the absolute value of the remainder, and then we know the error is plus or minus that value, right? So we're off within 1%. We're within 25%, right? So this is going to equal, right? And the way you solve for the remainder is you subtract Pn from both sides. So this is going to equal the absolute value of the original function minus your finite polynomial. So if I ask you what the error was, right, when we approximated those two values, we used our series. I think we used a 6th degree polynomial to find 0.1, and then we used a 4th degree polynomial to find ln of 1.1. Well, if you actually put ln of 1.1 in your calculator and you subtract off that big huge decimal we got, that's your error. That's how far off we were, okay? If you take cosine of 0.1 and you subtract off that big long decimal we got from our 6th degree polynomial, that's your error. That's what was left. So you take your actual value minus your approximate value to get the area, or get the error. But we can also calculate the error directly. And the reason you want to be able to calculate the error directly is because what if I need to know what value of n to go out to achieve a specific error? Like I need the error to be only 1%. So this notation looks a little nuts, but I'll explain it to you. The error term can be calculated directly using the following. Oops, this should be an X. Oh, I don't think it's supposed to be equal. It's just supposed to be between. So what we can do is, if you look at this, the only thing different, right? This looks like the nth plus 1 term of our polynomial, right? Because it says take the n plus 1 derivative, evaluate it at some value, put it over n plus 1 factorial, and then we know in the polynomial we would then multiply it by this term. But what's different here is z, okay? So normally if I actually wanted to generate the nth plus 1 term, I would evaluate that derivative at my value c. But what z is some value between x and c, right? Such that I achieve the desired area, or achieve the desired error, okay? So let's look at an example, and should always find that your z value is between your X value you're trying to approximate, and the C value you've centered at. And so what that Z is saying is you gotta be in the neighborhood of C in order to do this. Now Z is gonna represent the number we're actually approximating. So for our cosine function, Z would be 0.1 because that was the number we were trying to plug in. So you're gonna plug in that number into the nth plus 1 term and see what the error is. If we were doing our ln function, once again, the number we actually plugged into the function was 0.1. And that was, in fact, between 1 and C, okay? So let's look at an example of how you would do this. And this right here, guys, is the most important thing. Like, I'm not gonna really rake you over the coals on the exam about it. I probably won't ask you to calculate the remainder on the test, but like, just please keep these notes because this is the thing you're gonna be asked to do in like all your other classes when this comes up, all right? So let's look at an example where we want to determine how accurate our prediction was. So this is the third degree polynomial for sine of x. So we want to approximate sine of 0.1 by using P3 of 0.1 and determine the accuracy, right, of our prediction. This is a hugely important idea. So the actual value of sine of 0.1 says, well, we're going to take our function, our polynomial and plug in 0.1, and then everything else that's left, right, is our remainder. Oops. Right, evaluated at Z. So in general terms, right, what we're saying is sine of x is equal to our polynomial. Then the remainder says, well, and here's the thing to keep in mind. The subscript on the remainder matches the subscript on the polynomial. So what this is saying is this is the remainder after you did the polynomial at 3. But the remainder formula says go look at the next term, okay? And we know these terms are dramatically decreasing down to 0. So we're actually just going to use the fourth term to calculate that. So the remainder for this series would be f the fourth degree evaluated at z over 4 factorial times x to the fourth. And we need z to be some value between 0 and 0.1. But what was the fourth term? What was the coefficient of power 4 going to be here? 0. This derivative, right, was 0 at C, at 0. But notice we're not going to plug in 0 into that. We're going to plug in something else. So we will, in fact, get a value. All right? So let's look at it. So sine of 0.1 is going to equal 0.1, there's x, right, minus 0.1 cubed over 3 factorial. And this is 0.1 minus 0.000167, which works out to be 0.099833. So this is the approximate value because this is what came out of the polynomial. So our remainder, right, this inequality I've set up right here, right? If I take sine of all of these things or cosine of all of these things, right, it would preserve the inequality. So what we can say now is 0, the remainder has to be greater than 0. This is going to equal the sine of z over 4 factorial times 0.1 to the 4th. What's the biggest sine of z can ever be? 1, okay? So that means the remainder can be no bigger than 0.1 to the 4th, which is 0.0001, over 4 factorial, and that equals 0.1, 2, 3, 4, 5, 0.1, 2, 3, 4, 5, 4. So this implies, right, that sine of 0.1 is bigger than our approximate value because we know we didn't get everything, but no bigger than the remainder we calculated. So this was the approximate value. And this was the remainder. Oops. Oh, I did that backwards. Sorry, guys. 1, 2, 3, 4, 5. What did I write here? This should be a 3. So what we're saying is the approximate value was just from the polynomial, so we know sine of 0.1 is bigger than that because we didn't get everything. But the actual value of sine cannot exceed the approximate value plus the remainder. That would be the actual value. Yeah.
In R sub 3, in the parentheses, what's that supposed to be? It looks a little like a 3.
Right here.
No, up at the top. Z.
Oh, it's a Z. Sorry.
Okay.
I accidentally wrote a C, and it's supposed to be a Z.
Okay.
So what we said here was we were trying to find the low end of the value and the upper end of the value, and we knew that the remainder was more than 0. We knew we have a remainder because we only looked at 3 terms, right, out of infinity. So there had to be stuff left over. And then we said, well, we need to find the upper bound of this guy, right? Well, we know Z will never be bigger than 1, no matter what you put in there, because we don't know what value of Z we're going to actually use. So we said, all right, well, I just replaced Z with 1, so we know that that's bigger. Our 0.001 came from putting that to the 4th. The 4 factorial was here, so this is a good estimate for our remainder. And it's very, very, very small. So that's why we only have to look at the next term, because if I tried to look at multiple terms, the remainder would get smaller and smaller, and this number would get smaller and smaller the bigger degree our polynomial got. So what we said is the true value of sine of 0.1 is bigger than our approximation, because we knew we didn't get everything, but no bigger than the approximation plus the remainder. And so if you go back and look right here, what did we say the approximation plus the remainder was? The exact value. So we're saying that our exact value was less than this guy, which was our maximum error. So if I actually add this ridiculous number together, what you now get, if we add the right side, we get our final inequality that says the value of sine of 0.1 is between this number right, and this number. So this is why I had to go out so many decimal places. Because we had to go 1, 2, 3, 4, 5, 6 decimal places after the decimal before we could even see a difference in those two numbers. So this is why, too, I was saying when you get into like